Hey folks, we're continuing through section 3.1, ionic compounds. This is part 2. So we left off looking at these three questions. And so we've already kind of answered them in the first part, but we're going to hit them again from a different way. So what are ions? And then also importantly, why do they form? And why do ionic compounds then form? Okay, so what are ions? Well, remember, ions are atoms that have lost or gained an electron. They have a charge, right? And we know the equation for that charge. We found this ourselves. The number of protons minus the number of electrons. If an electron is lost, there's a positive charge left over, and this is called a cation. If an electron is gained, we have an excess negative charge, and this is called an anion. So just as a review, right, there are three subatomic particles, protons, neutrons, and electrons. If there is a change in the number of protons, that changes the atomic number. That's a different element. If there is a change in the number of neutrons, this changes the mass. These are called isotopes. If there's a change in the number of electrons, this changes the charge, and these are ions, right? And remember, this is because protons have a positive charge and electrons have a negative charge. So a cation is an ion with a positive charge, has fewer electrons than protons. And an anion, an ion with a negative charge, more electrons than protons. So next question, why do ions form? Ions form in order to produce the same electron arrangement as a filled shell, or that would be as its nearest noble gas. And the noble gas electron arrangement is the most stable. So a filled shell, good. Nature likes that. Here's an example of sodium. Just sodium, regular old sodium atom. And remember that it's element number 11. It has 2 electrons in the n equals 1 shell, 8 in the n equals 2, and 1 out there by itself in the n equals 3. And that one electron is valence, right? So sodium, uh, if it loses that one electron for whatever reason, what's left over is sodium plus the sodium ion, and we see that one valence electron is gone, and what's left is just complete shells of 1 and 2, which looks electronically identical to neon, which is a noble gas. It's a filled shell arrangement. So metals tend to lose electrons, which results in the positive charge in the cations. Okay, now if we move over one element to magnesium, down here at the bottom, magnesium has 12 electrons, and so now it has 2 up here in the n equals 3, 2 valence electrons. So if it loses both of those, it now has a +2 charge, and it has the same electronic structure as neon and as sodium plus. After magnesium on the periodic table would come aluminum, and you guessed it, it has 3 electrons in the n equals 1, and if those 3 were to be lost, it would be aluminum with a +3 charge. So far we've seen 1, 2, and 3 valence electrons are lost to give a charge of +1, +2, +3. Okay, and remember the groups on the periodic table and the periodicity, that instead of sodium, magnesium, and aluminum, we went down a row to potassium, calcium, and gallium. It would simply be shifted up to the next energy level, otherwise identical. So what I mean by that is, here's sodium, right? If we look right under sodium, it's potassium. And potassium has a total of 19. So it'd be 1, 2, and then 8, and then another 8, and then 1 up there in n equals 4. And the n equals 4 would be lost. You get a plus 1. So the trend is groups 1a, 2a, and 3a lose all of their valence electrons. Then the charge on the cation is equal to the group number, right? So a 1a atom becomes a cation, the plus 1 charge. And 2a becomes plus 2, and 3a becomes plus 3. And then the resulting electron arrangement is the nearest noble gas, which is the previous noble gas, the one from the prior row. Okay, so the transition metals and group 4a metals are a little bit different. Now, they don't always lose all of their valence electrons. This charge is much less predictable. You can't necessarily know in advance. And so we're not going to do a whole lot with these, but I do want to introduce the topic. So some of these metals and the transition metals in the middle of the table, the non-main group, can take different charges depending on how many electrons they lose. Now, they do still lose electrons, right, because they're metals. So they do still make positive charges, but sometimes they can form more than one. And if so, we use Roman numerals in the name. So for example, iron plus 2, which would be an iron atom which has lost 2 electrons, has the name iron, parentheses, Roman numerals 2. This is important when we start to name ionic compounds. So iron plus 3 also exists, and it's lost 3 electrons. It's a different ion. It's going to behave differently. So it'd be iron, parentheses, 3. Now, just because it's a transition metal doesn't mean that it always has Roman numerals. For example, silver only loses 1 electron, and so it's always silver plus 1. So Ag plus is the silver ion. Zinc is always 2. Zinc 2 plus is the zinc ion. You don't need the Roman numerals. Let us continue our trek across the periodic table to groups 5a, 6a, and 7a. Now these will form anions. Okay? These are nonmetals, and they become more stable by gaining electrons. They gain electrons to fill their valence energy level. You can think of at 5, 6, and 7, it's more than half full, and it's easier to fill it than to remove. Okay, so let's jump down here to look at fluorine, which is in 7a, right? So it has 2 electrons in the n equals 1, and then it has 7 electrons in the n equals 2. So to find the nearest noble gas, right, it could, or to find a noble gas, could lose all 7 and take a plus 7 charge, or it could gain and take on an extra electron and just take a minus 1 charge. Basically, you want to find the route that has the least amount of movement of electrons, and so adding 1 more is easier energetically than removing 7. And so if we add 1 more to get F minus, then it looks just like neon. And it looks just like sodium plus, remember, or magnesium 2 plus. The difference is the number of protons, right? So the charge of a 7a anion is minus 1. So the magnitude of the charge on the ion can be found by taking the group number minus 8. Okay, so here's another example. Oxygen right next to fluorine, right? It has 2 electrons in the 1 equals 2, or n equals 1, and 6 electrons in the n equals 2. So if we add 2 more here, it would have a filled shell that would look just like neon, and it would have a charge of 2 minus. So it is in group 6A. So group 6 minus 8 would be minus 2, and that's the pattern. Here's a way of visualizing the periodic table with charges. So if there are multiple charges, like on some of these transition metals, you can see them listed here. But most only take on 1 charge. And now the pattern is clear if we look down a row, or sorry, down a column. +1, +2, +3, -3, -2, -1. And we haven't really talked much about this one, where carbon is. Right, it's right in the middle, right? It could, it's half filled, right? And so it actually doesn't form ions. Carbon very rarely forms ions. We're looking mostly at 1, 2, 3, and 5, 6, 7. Remember again, 8A doesn't form ions either because it's already a filled shell and it's happy. So we might write something like this on our periodic table, looking at the common charges by group on elements when in ionic compounds. Okay, and we will leave it at this for now and come back for part 3 to continue and talk about forming ionic compounds from ions and naming them.